We started off the whole statistics section talking about computing averages. We focused a lot in the last couple of lectures on properties of computing averages, how to estimate the variance of an average, the standard error mean, right? SEM. And there's a lot of times that's kind of where basic statistics stops. And it's like a bridge. I think of it as a bridge. It's a connecting point. All of this stuff about averages and how they converge and what the error looks like, and what the variance looks like. All of that has one foot on the side of descriptive statistics. These are just summaries of data. You take your data, you average it. And I think when we introduced this, we expressed the idea that this was a revolutionary concept when it was first introduced. The idea that you should average together measurements in order to get something better, was a weird idea. So but it sort of emerges as just a way of describing or summarizing data. And now we're going to take a step beyond that, and we're going to just basically reinterpret that and generalize it. And the generalization goes like this. Most of the time, in fact, in real world problems, in real science problems, the thing you're measuring is not exactly what you want. That is, you're not making a direct measurement of the thing you want. And for many of you working in cognitive or neuroscience, you're going to be thinking about how some observed behavior relates to, I don't know, some sort of response in MRI voxels or something that a neuron is doing. We're going to look at what an animal is doing and think about how its neurons are related to its behavior. And you're not going to be thinking about, I just want to measure the average behavior, or I want to measure the average neural response. You're going to want to connect these things. You're going to want to build a bridge that connects them. You're going to want to describe them with some sort of model. So you'll make a hypothesis about how these things are related or what it is that the neurons are representing. And normally, that thing that you'll be hypothesizing about is not going to be directly measurable. You're not just going to go measure it and then average together your measurements to get the answer. It's going to be indirect. You're going to have to infer the thing that you want from the data, but that inference will not just be a matter of averaging data together. So the general problem that you face, the inference problem, we've already mentioned that word, inference, is something that is what statistics really broadens out to cover. And the sample average, and the way as a way of estimating the mean, is just a very special case. It's a prominent case. It's the one that you hear about the most. It's the one that you see examples of all the time. And it's the one that you learn about in introductory statistics. So we're now making a step to the other side of this bridge that I mentioned, and we're going to talk about more generally how you estimate things that are not just averages, and we'll talk a little bit about procedures for doing those estimates, and we'll talk also about how you get confidence intervals, how you express your uncertainty about the estimates that you have, even in the cases where they're not just simple averages. Okay, so we'll think about in general, we're going to think about estimation. We're going to estimate some parameter. An estimate is just a function of the data. So we're going to collect some data, and I'm going to compute some function on the measurements that I made, and that function is going to hand back my estimate, the thing that I want. And that's supposed to give me the true value of something that is causing the system to behave the way it is. And what I have to do is now reason about how close am I to the true value, how well does this, if I assume that that is the true value, how well does it explain the data? How would I go about comparing if I have different models that use different constructions for describing the generation of the data? How would I compare them? How do I decide which model is better? What measurements should I make? What additional data should I gather to make that decision and decide which model is better? So all of those are questions that statistics addresses, and basically from now until the end of the course, we're going to be seeing examples, sometimes special cases, sometimes general descriptions of those kinds of problems. Okay, so today we're going to start with the most basic form of estimation, aside from just sample averages, and we're going to talk about it pretty generally, but I'll show you a bunch of examples. Okay, so this is just a few things to get out of the way up front, and these are a little bit sort of frequentist in their notion, but we're going to quickly switch over to a Bayesian mindset as we go through the lecture. Okay, so it's very common that people describe the quality of estimates using mean squared error. That we already know that we have lots of reasons that we've talked about right from the outset why we use squared error, the advantages that it has, the fact that it can be computed in closed form, that we know how to manipulate it and understand how it transforms under affine transformations, the fact that we can do it in multiple dimensions and just use linear algebra to figure things out. So all of those beautiful properties and facts lead us to this fact that we often describe the quality of estimates using mean squared error. And we also, we've shown you, although you may not recognize it in these phrases, we've shown you that you can partition mean squared error into kind of two pieces. There's sort of a mean, and then there's the variance, right? So there's the way this gets written for estimation is the mean squared error is the variance of your estimator plus the squared bias, right? So we've written this kind of thing down actually multiple times. It comes up in slightly with different words, but it's actually the same math every time. The math is just simply the fact that if you subtract off the mean, if you write out the sort of squared errors, you can partition those squared errors into two pieces. One is how much they're off on average, that's the mean. And the other piece is how much they fluctuate, that's the variance, right? And if you add those two things together, you have to square the mean error. That's called the bias. You square that and you add that to the variance, and that's the mean squared error. Okay, so already this tells you that if mean squared error is what you're trying to minimize, you have to kind of jointly or simultaneously minimize both of these things. These are both positive. Variance is a positive quantity. The bias could be positive or negative, but you're going to square it. So these things are two positive things, and you're generally trying to get that to be small. And in general, estimates, when you come up with a way of computing an estimate, it's going to be of interest to understand, is it biased? What does that mean? That means that if I were to run this procedure on data, does it, on average, give me the right answer? If on average it's always a little bit too low, that means it has a negative bias. If on average, if I were to repeat this procedure 1,000 times on different data sets, if on average it gave me an answer that was too high, it would have a positive bias. Unbiased means it has zero bias. That is, on average it gives the right answer. That's not a statement that gives the right answer on any particular set of data. This is a sort of, this is a theorist's statement, right? That if it's the right model, and you were to draw samples of data from that model, then this procedure, on average, will give you the right answer. Okay? So that's the bias. And then the variance is, again, how spread out it is. And so it's very often, it's useful to partition the properties of an estimator into those two pieces, the bias and the variance. Classical statistics, if you actually look back through the long history of the literature, there's a lot of emphasis on trying to find estimators that are unbiased and minimum variance. So the idea is, instead of saying, oh, well, I just want to minimize the mean squared error, which is some sum of these two things, people partition them into two pieces, and they say, actually, the bias is really bad. I would like to have an estimator that has no bias, because bias is really bad. Why? Let me just ask you, why is bias so bad in let's say, an experimental situation? Let's say I'm gathering data, I gather 50 data points of some measurement. Now I run my estimator, or I have two estimators that I'm considering, and let's say they have the same mean squared error, but one of them has a high bias and the other one has a high variance. Which, in general, is there a way to prefer one or the other? Why is it that in the field of statistics we actually kind of would prefer to have things with minimum bias or zero bias? Anybody want to guess? Go ahead.
You can detect the high variance without knowing anything about the ground truth, but unbiased would be invisible.
Excellent, yes. So that is the answer. The answer is that variance is easier to assess. We often have, we have ways of measuring variance, or of estimating variance, at least approximating it. So when you run an estimator, you can kind of get an idea of what the variance is. And we're going to show you a bunch of ways to do that. And that's how you get error bars or confidence intervals, or that's what the standard error of the mean is. The standard error of the mean is an estimate of the variance, right? Bias is much harder. To really assess the value of the bias, you have to know the true value of the thing out in the world. So let me put it another way. I'll just give it to you in a sort of cartoon form, right? If I want to know if my estimator is, what the variance of my estimator is, I could imagine just running it on different data sets that are drawn from the same source. And I can just look at how the estimate bounces around and measure how much variability there is. But what if I want to know if it's biased? If I don't know the true value of the thing, then I have no way to assess whether my answers are biased or not, right? Because without knowing what we might call ground truth, the true value of the thing I'm trying to estimate, I don't know whether I'm coming out too high or too low. But I can tell how much I'm flopping around as long as I can repeat the experiment. Okay, so we have ways of assessing variance, but we don't really, in many cases, we can't really assess the bias. So bias is considered really bad in traditional statistics, and the general rule in traditional statistics is to look for things that have either no bias or very small bias, and then work on squeezing down the variance. Okay? All right. A more modern view often sort of steps away from that and says, well, I want to really trade them off against each other, and I want to use model selection, and we'll talk about this as we go down the path, and various procedures for sort of trading them off or making decisions about bias versus variance, and I'll need ways to select and to govern that trade-off and make choices about where I want to be. Okay, so these are too many words for this slide. We're going to hit all of these points later, so I won't say anything about it now. Okay, we're going to talk about how to estimate variance a little later. Okay, so now let's introduce the main thing that people use as a form of estimation. This is the most commonly used statistical estimator. It generalizes the sample average, which I'll show you in just a second, and it's very simple to describe, but it's actually kind of subtle and difficult to really understand fully. So what is it? This thing is called the maximum likelihood estimator. The sample average is appropriate when you have direct measurements. I already told you this. But if you don't have direct measurements of the thing you're trying to estimate, you often need to express what's the relationship between the thing you want and the thing you're measuring. You got to have that, right? How else can you estimate something if you don't know how it's related to your measurements, right? So once you've expressed that, that expression is usually a probability. And the probability is the probability of observing a data point. Let's imagine your data are vectors, okay? So this is the probability of observing a data vector given theta, and I'm going to use theta as the variable for the thing that I would like to estimate. Okay, that's the thing I care about. That could be just the mean of some distribution. That would be the simplest case, and everything will kind of go back to sample averages. Or it could be some parameter of some complicated model, or it could be a whole vector of parameters, right? A bunch of parameters that describe the behavior of some system, and what I'm trying to do is make observations of the system. Let's say I'm recording neural responses from 10 neurons, and I have a model, a description of how those neural responses are related to what a monkey is thinking about when it's planning a decision or an action. And I'm going to use this procedure to estimate the parameters of that model. Okay, so the parameters are theta, and the measurements are x. Okay, this thing is a conditional probability distribution, the probability of the data given the thing I want to estimate. And what we're going to do is we're going to rename this. Instead of calling this conditional probability of the data, I'm going to call this a likelihood function. So that sounds weird. Why am I taking that, which already has a name and an interpretation, and giving it a new name? The way we think about this is that the theta is fixed for a given theta. Here's a probability distribution over x, right? So that's what that vertical bar means, given or conditioned on theta. The distribution of x, probability distribution of x, conditioned on theta. That is, you're pretending that you know theta. And then if you know theta, this tells you what the distribution of x looks like. We're going to think about it backwards, because actually the situation we're in when we're trying to do estimation is the other way around. We have x, we just measured it, and we want to know theta. We do not know theta. We wish we knew theta. and we're going to try to estimate theta, but we don't know theta. So in fact, we have to read this conditional probability backwards. When you read it backwards, we give it a different name so that we can remind ourselves that we're thinking about it backwards, and we call it a likelihood function. This all sounds a little bit bizarre, and we will fix it toward the end of today. But this is the tradition and the history of this. This thing is labeled and called a likelihood function. And when we call it a likelihood function, what we mean is we're thinking of it as a function of theta with x fixed. That's very weird because x is supposed to be a random variable. But we're going to hold x fixed. It's not a random variable. It's a fixed set of measurements. And we're going to assume that we have those, and we're going to think about this as a function of theta. So that's a likelihood function. Okay? So the procedure, you can just guess from the name of it, maximum likelihood estimator. What you do to find the best theta is you just maximize this thing, interpret it as a likelihood function. That is, you're not maximizing it over x. X is fixed. That's the data. You are maximizing it over theta. What is the theta that gives me the largest value of this? It's a slightly weird thing to do, and we'll explain a little bit more why. But this is the procedure. Okay? So if you want to get mathy and write it out, it looks like this. So what does this say? Theta hat. Why did I put the hat there? I'm not talking about theta in general here. I'm talking about the estimate of theta. Theta hat is my best estimate of theta. It's a function of the data. So this is, in curly braces, imagine that I measure multiple data points. So there's multiple vectors. They're indexed by n. So I have, just think of this. Think that these are vectors in 2 dimensions. So each of these is a 2-dimensional vector. It's a point in some space. Here are the xn's. They were drawn from some urn, p of x given theta. My job is now to go the other way. Given x, I want to go back over here and figure out what was the theta that produced those x's. Not one x, multiple x's. That was the points are, right? Okay, so there's a set of x's, and what do? I'm going to assume that the points were drawn independently from that urn, and the joint probability distribution of all of the x's that I've observed is, of course, just the product of their individual probabilities, i.e. the product of their individual conditional distributions, right? So that's what this is. This is a product. I take the product of the probabilities of all of those guys, multiply them together, and then I want to maximize that. So I do max over theta, and the arg is there to remind us that we actually are not trying to find the minimum value of the probability. What we're trying to find is the theta that achieves the minimum value, right? That's what the arg means. I'm not interested in some function I'm minimizing, right? I'm looking for the, or maximizing, sorry. It's a function, I'm looking for the peak, the highest point, but I don't care what the value, how high the highest point is. I care about where is the highest point. That's what the arg is telling me, right? Okay, so I'm trying to find the theta that maximizes that. And when you maximize a function, you can equivalently, you can take that function and run it through a monotonic nonlinearity. Right? So if I take a square root, if I want to maximize something, I could just as easily maximize its square root. I won't get the same value in terms of the height, but I will find that the position where the square root is maximized is the same place that the whole function is maximized. And I can also, for example, take a log. So it's very, very common when you're maximizing likelihood that you don't maximize the likelihood, you maximize the log likelihood. So sticking a log in there, you'll see why in a second. Putting a log in front of it is a very, very common thing to do. In fact, what I didn't put on the slide, but is also very common, is to flip the sign. So instead of just taking the log, you take the negative log. And you will see the phrase negative log likelihood frequently. Many people will try to, instead of maximizing the likelihood, they will minimize the negative log likelihood. So there's nothing subtle here. Each of those steps is very simple. What you've done is you've taken a log. Well, argmax of something is the same as argmax of its log, so you didn't really change anything. And then you flip the sign, so you have to switch from maximizing to minimizing, right? Because now the peaks become the valleys and the valleys become peaks, so you got to flip your head around and look for the minimum. So you can either maximize the likelihood or you can minimize the negative log likelihood. And that's actually very common. When you find examples of this in the literature, or you see things in people's papers in their method section, they'll often say that we minimize the negative log likelihood. Okay. So I probably should have put another line here, but more notation. Who needs it? Okay, one other thing to note is, it's obvious, but I want to make sure that everybody sees it. When you take the log of this whole probability, it's a product. The log of a product is the sum of the logs. So the product becomes a sum, and the log moves inside. Right? So that's another little trick that's going on here. So, and part of the reason why we like doing this in the log space is that the product is kind of a pain to deal with. But if you think about optimizing, how do you optimize, right? You might, for example, take the derivative of this thing and set it equal to 0. That's one way how you would find a minimum or a maximum of a function, right? So just take the derivative and set it equal to 0. If it's a multi-dimensional function, you would take the gradient and set it equal to 0. But if it's a product, it's kind of a pain to work through differentiating a product. It's a sum, it's actually much easier because the derivative of a sum is just the sum of derivatives. The derivative is a linear operator, actually. So it commutes with the sum. You can apply it to the individual terms and add them up at the end. So if you can write it as a sum, it's going to be easier to differentiate. Okay? So that's one reason why the log is there. You'll see that if you stick a Gaussian in here, in fact, you can kind of imagine, if this function is a Gaussian, this probability distribution, it's e to the minus. I guess I'll write it. If you have e to the minus x squared over 2 sigma squared, and now you take the log of that, right? Now you've got minus x squared over 2 sigma squared. That's much nicer, that's quadratic. And now you can flip the sign, so the negative log likelihood is going to look like that. I left out the normalization factor, so there's a root 2 times sigma here. There's a pi in here somewhere. Where's the pi go? Somebody help me. Root 2 pi?
Yeah.
Sound right? It's under the square root.
Yep.
Yeah, okay. So technically, when we take our negative log likelihood, we've got to include that. Why am I bothering? We often ignore the normalization constant. Why am I putting it in now?
Because sigma is the parameter.
Could be, yeah. Does that look right? Yeah. They're both, when I take the log, this has a minus sign in it, and this will have a minus sign in it also because it's 1 over this. Log of 1 over is negative the log of the thing. And then I flip the signs because I want the negative log likelihood and LL, and that gets a plus sign. Okay, so now you have an expression that you could use, for example, to estimate sigma, right? I could look for the sigma that maximizes this expression when I substitute in my data, the x's. In this particular example, the sigma would be theta. That's the thing we're trying to estimate. Okay, so the point is that logs often play nice with probability distributions. In fact, there's a whole family of probability distributions. It's called the exponential family. That are exponentials of different functions. Often they're polynomials. And for those families, taking the log is really nice because then you turn the thing into a normal polynomial and you can do calculations in a more direct way. Okay, so that's the explanation of what's on the screen. So let's see. Let's go through a few examples. I think that's what we're going to do next. We'll do the necessary coin flipping example. This used to drive Nathaniel crazy. He thought we should just obliterate coin flipping forever. Actually, maybe it was Pascal who was really driven crazy.
How can you obliterate coin flipping?
I don't know. I always said it's the most standard example.
Yeah. What you do?
It's the simplest probability distribution, right? Binary, 50%. Okay, so here's a classic example of trying to estimate the bias of a coin flip. And let's just think it through in terms of this likelihood concept, okay? And it's, well, I won't spill the punchline. So there's a coin, and we actually want to know whether it's a 50% probability coin or whether its probability is a little different than 50%. turns out that Percy Diaconis, I think it was Percy who wrote this. Didn't he write the article about coin flipping and bias? There's an article about the fact that flipping coins is not 50% unbiased in general. And he built a coin flipping machine. And he showed that if you flip coins kind of with about the average force that a human uses when they flip coins, there's a very slightly higher probability that the coin comes back landing the way it started. Slightly higher than 50%, and it's measurable. And it's kind of a crazy article, but it's worth reading. Okay, so here's an example of coin flips, heads and tails. And you all know, if you wanted to know whether a coin was biased, what would you do? There's a very natural thing that you would do, right? What would you do? I want to know if my coin is biased.
Flip it 20 times.
How many times? I want a number.
To flip it 1,000
You think, is there a fixed number of times that you should flip it?
I mean, infinity, like 80.
Infinity. That infinity is good. Not practical, but good. I like it.
It depends on the amount of bias you want to detect.
Aha. But you don't know the amount of bias you want to detect because you don't know how biased the coin is. You have a little bit of a chicken and egg problem, or a bias and variance problem.
It's like whether you want to make sure it's not biased larger than 1%.
Yeah, so I mean, you can think back to all those statistical tests that Mike talked about, right? Last time. You kind of want to flip the coin a little bit, and then ask, okay, what do I think the bias is, given the number of flips that I've done so far? So that would be an estimate, right? You would estimate the probability of the coin giving heads. That's and you want to know how close is that to 50%. But more importantly than knowing what the estimate is, what do you want to know? So I'm going to flip the coin twice. What's my estimate of its probability? There's only 4 options. If I flipped it twice and it gave me heads twice, what's my estimate of the probability of heads?
1.
I mean, if I don't know anything about coins and I flipped it twice and it gave me heads twice, I might just have to say, okay, this is a heavily head-biased coin. It always lands heads. I just did it twice and it ended up heads both times. If it gave me tails both times, I might have to say, well, it's a heavily tail-biased coin. And if it gave me one of each, I might say, oh, it's a perfect coin. It's right at 50%. But why would you know that those would be silly statements? Because you've only flipped it twice. Okay. So you flip it a bunch more, and you get a more accurate answer, and you do that by basically counting up the number of heads and dividing it by the number of flips. And each time you flip it, you're getting a little bit more information, and you're kind of homing in on what we've talked about, right? Sample averages, what do? They converge to the true mean, and this thing is going to converge to the true probability of flipping and getting ahead. But you need to know not just what's the estimate, but how confident are you in that estimate? What are the error bars? And that's what's going to allow you to make a decision that, oh, this thing is biased. It comes out more often heads than tails. You're going to have to be able to tell, think about null hypothesis testing, right? 50% is in the middle. You want to know, is my estimate deviating from 50% more than I would expect by chance? That's sort of the question you're asking. And so you need to know not just what is my estimate, but you need to know how confident you are about it. If your estimate is way out here and you're very confident, then you can state with more and more certainty that the coin is biased and it has a bias. It's this interval right around what you're estimating. Okay? So let's look at how that plays out. So after one coin flip, you calculate what is the likelihood of coin flips? How's that look? So let's think about likelihood. So theta is a number between this is a number between 0 and 1, which is the probability of this coin giving heads versus tails, right? And an unbiased coin has a value of theta of 0.5, exactly 0.5. X is, on one trial, is just head or tail. And this thing is equal to, well, if X is head, then the probability of getting head is theta. That's if X equals head. And it's 1 minus theta if X equals tail, right? And if I flip the coin once, what's plotted here is not the probability, the distribution over X. What's the distribution over X? X is binary. So the distribution, what does this distribution look like, just to be really clear, right? So if this thing is head, and this thing is, or let's do it the other way, I guess. We usually put the tail on the left. This is head, this is tail. The probability distribution is discrete and binary, and it's just two numbers, which, if it's a fair coin, are each 0.5. If it's not a fair coin, they're 3/4 and 1/4 or whatever. They have to add 1, of course. It's a distribution, a probability distribution. And in general, it's going to be, let's say, the way I wrote it over there, this is going to be theta, and this is 1 minus theta, okay? I just want to be clear how the notation relates to the problem. The X is a discrete, in fact, binary variable. Theta is a continuous variable that lies between 0 and 1. It's a parameter, but it actually is also a probability. And it's telling us whether heads or tails are more likely for this coin. Okay, so this is not the likelihood. This is the probability, p of X given theta. What's the likelihood? It's the other way around. I have to fix X. Imagine that I observed a head. So I'm in this condition, X equals head. And now I have to plot what is this thing as a function of theta. So what is this thing as a function of theta? Well, it's theta. That's this. Okay, so after observing one coin, the likelihood looks like this. After observing another coin, and by the way, I mean, it's sort of funny. What's written here is the conditional probability, but we're thinking of it as a likelihood. The heads is the fixed variable, the X is the one we're plotting, right, against. Okay, so it's this, and of course, if I observe a tail, what is the likelihood? Well, it goes the other way, 1 minus theta. So that's that, okay? So these are, again, continuous functions, because theta is a continuous parameter. It lies between 0 and 1, and that's what the likelihoods look like. And of course, what happens if you flip more coins, we can make a table which expresses the number of heads on this axis, the number of tails on this axis. Unfortunately, it's kind of upside down, so the tails are increasing this way. It should really go the other way. I keep meaning to flip this, but I didn't. And then you can sort of think about, well, if in a given observation situation, i.e. with a given set of data, where the data we're considering are only somewhere between 0 and 3 heads and somewhere in between 0 and 3 tails, what does the likelihood look like? And another thing to point out here is that if you go across diagonally, the number of coin flips is increasing. So in the far upper corner, that's no coin flips. And if there are no coin flips, technically there's no likelihood. We don't have any data. So we're going to talk about what should go there. There's something stuck in there. We'll talk about it in a few minutes. But for now, just ignore that. If I measure one coin flip, I'm now in these two boxes. And my likelihood is either, I already showed you this, a ramp down or a ramp up, depending on whether my observation is 1 tail, 0 heads, or 1 head, 0 tails, right? Those are those two boxes. Now I go to the next case and I flip the coin twice, 2 coin flips. Now I have 3 options. It's 1, 2, and 3. It's these 3 on this diagonal. This is if I have 2 tails, no heads, 2 heads, no tail, 1 of each. Of course, this is a more likely outcome, 1 of each. But what we're interested in here is the likelihood function. And remember that our job, if after we flip 2 coins, is to just pick off what? the maximum, right? The thing that maximizes the likelihood, maximum likelihood estimator. So we're going to pick off the maximum of this function, and it's kind of what I told you as a story about 5 minutes ago. The maximum of this function is on the far left. It's at 0. If I observe 2 tails and no heads, then I'm going to assume that the coin has a probability of 100% tails. And if I go over here, it's the other way around. It's 100% heads. And if I'm here, it's right in the middle, 50%. These are kind of silly estimates. But that is what comes out of this procedure. Go to the next one. There are 3 coin tosses. And you can see now that these shapes are getting a little more interesting. And they are actually, if you think about it, these are just polynomials, right? Because each time I'm either multiplying theta or 1 minus theta, depending on whether I flip a head or a tail, right? And so I'm multiplying either by a ramp or an inverse ramp. But in the end, if I multiply all those things out, I'm going to have a polynomial in theta. It's going to have some constant term and a theta squared term, a theta term, a theta squared term, a theta cubed term, and depending on how many coin flips I have, it'll go up to whatever order. So this thing has cubic terms, this one has quadratic terms, this one goes up to quartic terms, etc. As I go further and further down this array, this thing sort of, what's not shown are the other corners of the array. It's kind of, we're chopped off. There's other possibilities here. If you follow this all the way down to this corner, the only example with 6 coin tosses is this one, and it's assuming that they're 3 and 3. But there's another one that should be here that would be 2 and 4, and this one would be 4 and 2, etc. And so in all of these, you can see that the likelihood, the peak of this likelihood, is if you go along the diagonal, it's always in the middle. It's exactly at 0.5. But if you look at these other options, it's a little bit off of 0.5. Right? So this one is to the left, this one's to the right, to the left, to the right, etc. Okay, so this is what the likelihood is going to look like for many, many different possible data configurations. And the estimate is always just to pick the peak. And it does, what's going to happen is you can kind of imagine this is a typical flip sequence. We should put some more on here. But if you plot the proportion of heads measured so far in the sequence, you start flipping the coin, flipping the coin, flipping the coin, and you observe head, head, and then there's a tail here. But what's plotted is not whether it's a head or a tail, because that would just be binary ping-ponging back and forth between, let's say, 0 and 1. What's plotted here instead is the fraction of heads as a function of the total number of flips. And you can see that that thing is bouncing around quite a lot in the beginning, but it very quickly kind of settles in right around this 0.5 dotted line. And it sort of oscillates around it, but these oscillations, this variability is getting smaller and smaller and smaller and smaller as you go out. Okay? So it's kind of, this is just a picture to show you what you already know, which is your estimate of this thing is going to converge. It's going to stabilize. The more you flip the coin, and it's kind of, this is the infinite coin flipping request from the back, right? So what we'd like is to just go out forever, and then the value of this thing will stabilize at the correct value, and then we can say, yes, it's 0.5, or no, it's a little bit off of 0.5, for example, 0.494. Okay, but we can't wait for an infinite number of trials. We're going to have to stop somewhere, and that's true in all scientific experiments. You are going to deal with limited data. The more complex the experiment, and the more difficult the thing you are trying to control, the more variability you will have to deal with. And the more complicated your model and the more parameters there are, the more potential for variability there will be. So working with a multidimensional case is even harder. You need even more data to constrain the parameters than you do for a simple one-dimensional case. So in fact, you always have to deal with variability. It's not something you could go away by just collecting infinite data or even giant amounts of data. Usually you're going to have to put up with the fact that you're flopping around. Okay? So that means you need to know not only what is my estimate, but how much am I flopping around? What is the variability? And that's really the trick. You report both the estimate and some measure of the flopping around. And of course, this goes back to the beginning when we talked about sample statistics and summary statistics, right? The idea that you want to express something like the central tendency and the dispersion, right? right? I want to know not only where something is, but how much it flops around that, okay? So that's what we want here. All right, so let me, so how does this work for the coin flipping case? Well, this is unfortunately different notation again. So I think Mike introduced this, and I gave you this expression, right? So this is here, theta is p head, the way I wrote it on the board. That's the probability of heads. The n and the m here are indicating if I've observed n heads out of m flips, okay? And then the total if you want to write the likelihood, it's theta. The way I wrote it would be theta to the n, which is the number of heads observed, times 1 minus theta to the total number of flips minus the number of heads observed. This is the number of tails observed. Okay? So it's just, all you're doing is multiplying these probabilities. So this just goes right back to the initial slide I gave you for maximum likelihood estimation, right? You write down this probability for each trial, and then you multiply them out over all the trials, and you're going to get that thing. Okay. So now we want to do maximum likelihood estimation. So how do I maximize this? I want to maximize this over what? I could do the negative log likelihood, right? And minimize it. So I want to do arg. Should we do the max or the min? Should we do the log or not the log? Anybody want to chime in? Do you think it would help us to take a log here? Anybody think yes? Why would it help us to take a log? We don't have to take a log. Our job is to optimize this. We want to compute, we want to basically find the maximum of this thing. We're going to do it by taking the derivative and setting it equal to 0, the old-fashioned way. And the thing we're taking the derivative with respect to is not n or m. It's the thing we're trying to estimate, which is in this slide, p sub head. Okay, but on the board, I'm going to leave it at theta. Right, it's a notation switch. Okay, so it's theta because that's the way we've been writing it out for the maximum likelihood estimator. So I want to compute the derivative of that thing with respect to theta. So let me just write the thing that I'm trying to compute the derivative of. And is it going to help me to take a log? Yes or no? Do we have consensus? Maybe. Why would it help us to take a log? Anybody want to say?
It's a product.
It's a product, and the thing that we care about is this thing, but it's raised to a power. We take a log of that, that power is going to come down and just be a multiple, and that's going to make it easier to deal with. So let's do, we can leave it as argmax, we won't negate it, we won't bother. But we're going to do log of the product of, it'll be theta to the, I just want to make sure I'm more or less captured. I'll stick with the n's and the m's. So it's theta to the n, and it's 1 minus theta to the m minus n, right? And I'm going to take the log of that. It's a log of a product, so that's the sum of the logs.
You dropped something?
What did I
Say
drop?
why?
Oh, the m choose n. Is that what you're
Why
talking
is there
about?
a product over there?
Sorry. You're right. We don't need the product because it already is a product. Apologies. I'm trying to jump too many steps. Just the log of that. This already is the product of all these things. And that's fine. And there's technically, we have the m choose n out in front. Right? Or is it n choose m? No, n choose n. It's that backwards, actually. The way this is written.
I thought it had it both ways in the previous
n
slides.
it's n choose m is the total. Anyway, it's not going to matter. This
No,
is a function of n and m.
Your notation there is n head, so you're stuck with that. M choose n, please. Actually, it's entries and head.
Doesn't
Which
matter.
one is the total and which one is
It's not going to matter. Look, this is a log of a product of three things. The first thing has no theta in it, and we're optimizing over theta, so it is not going to matter. The second thing has a theta in it. Good, so let's put that in, and that's going to become n times log theta, right? The third thing has a theta in it, so that's going to be m minus n times log of 1 minus theta, right? I'm just taking logs of these things. It's a product of three things. I separated them out into sum. Okay? And that's what I want to maximize. So now let's differentiate. Take the derivative with respect to theta. And what do I get? Anybody remember what the derivative of log is? Right, so I'm going to get n over theta. I'm going to get n minus n. Derivative of that is going to be what? I get a 1 minus theta, and then I have to take the derivative of the argument of the log, and so I'm going to get a minus sign, right? And I have to set that equal to 0. Sound okay so far? Okay, so now what? Put this term on the right, multiply through by theta, multiply through by 1 minus theta, right? So I'm going to get n times 1 minus theta. Sometimes you might know that as cross multiply, right? Is equal to m minus n times theta. Now I multiply all this out, I can see I'm going to get an n minus n theta here. And I'm going to get an m theta here, minus n theta there. The minus n thetas are going to go away. Minus n theta. So I'm going to get theta equals n over m. Or I guess I'll write theta hat, because that is the optimum. Well, that's convenient. All that work, well, it wasn't that much work, but all that work, and it comes out to be like exactly what you would have guessed. How would you think you would want to estimate theta, the probability of heads? Well, you might take the number of heads you've observed and divide it by the total number of coin flips, and you might say, well, that's a pretty good estimate of the probability of heads, and you would be right. That's a pretty good estimate of the probability of heads. That's exactly what it gives you. Okay? So it gives you, in this case, something that's completely obvious and you could have guessed in advance. But it's nice to know that this is the maximum likelihood solution. I'm going to tell you, I haven't given you technical things about maximum likelihood, but I will in just a moment. There's a reason. So why do you want to use maximum likelihood? A, it's standard for the last 100 years. You're writing a paper, you say, I have to estimate the parameter of my model. How do I do it? I compute the maximum likelihood estimate. That already saves you having to write out a couple pages of stuff about how you did your estimate, because you just in one line said, I did the standard thing, and everybody knows what that means. Second, it comes along, the reason it's the standard thing is it comes along with a lot of nice properties and guarantees, which I'll talk about in just a moment. And so you could sort of rely on certain things that are going to be true of maximum likelihood estimates. And if you make up some other estimate, and by the way, this is not the only way to estimate a parameter, you can make up whatever you want. Any function you want, you can say this is my estimator and I'm using this because I like it. But you're responsible when you do that to say something about why it's a good estimator, and usually that means saying something about its properties in terms of bias and variance or accuracy, and especially bias and variance on limited amounts of data that are the kind that you're working with, right? So you have this obligation, if you're going to make up an estimator, to say something about it. If you just use the phrase MLE, then you don't have to say much about it, because everybody knows about that one, and they assume that that's a good choice. It's not always a good choice, but that's kind of a very common assumption. All right. By the way, in modern machine learning, we use all kinds of different procedures for doing optimization. So one of the things that happens is you don't sit down and write out a little bit of calculus and get your answer and say, aha, here's my estimate. What happens in complicated problems is often that this optimization, argmax, is not something that you can get in closed form. You cannot write down the answer. So how do you solve it? Well, you implement on a computer something that computes your function, your likelihood function, and now you have to do a numerical procedure, an iterative procedure on the computer, usually something related to gradient descent. So the computer will calculate, you're going to hand your computer the function. The computer will calculate what are the derivatives of that function. If it's a multidimensional function, it will calculate gradients, and it'll try to move uphill, or if it's the negative log likelihood, it'll try to move downhill until it gets to the bottom, right? And then you'll run into all kinds of issues about whether it can get to the bottom, how long does it take to get to the bottom, whether it gets stuck somewhere. All kinds of issues will come in about the numerics and the algorithm that is used to solve for the optimum. So if you can get it in closed form, you're better off. Because now you don't have to argue about, well, I chose this algorithm with these kinds of step sizes and I put these extra things in here to make sure that I didn't get stuck. You don't have to do any of that. You can just say, hey, here's the answer. And I just computed this. So I'm giving you a little bit of a preview of like some things that we're going to bump into. When we go further down this path, we're going to run into things that we cannot compute in what's called closed form. We can't write down the answer. We will have to actually compute them by optimizing them numerically. And modern machine learning rests on numerical optimization. Almost everything that people do is numerically optimized because the problems are too big and too hard to do in this way. But that doesn't mean you shouldn't try. And for many problems, simpler problems in data analysis and understanding of how to fit simple models, doing something in closed form is really a better bet if you can come up with such a thing. Okay. All right. Here's another example.
With a bug in it.
Oh, excellent.
E to the minus lambda.
Oh, great. Okay. Well, we also should be rewriting these with theta instead of different notation. Lambda p head. Okay. So here's another example. This is Poisson. This is relevant to those of you that are studying neurons. So a simple description of neural spiking. So you measure the count, the number of spikes that a neuron fires in some small time window. You might choose 20 millisecond time window, 30 millisecond time window, whatever it is, 50 milliseconds. You count up the number of spikes. And a very common assumption is that the number of spikes that fall in that window is governed by some sort of rate. That is, the neuron under these experimental conditions that you're recording, the neuron has some drive that is trying to make it spike, but the number of spikes that it produces in that window, if you run the experiment multiple times, will not always be the same. It'll fluctuate. And the distribution of spike counts, so this is again a discrete variable, just like this binary coin tossing example. The distribution of those spike counts follows something close to a Poisson distribution. So Poisson distribution is a very standard distribution that people use when they're describing things that are arriving randomly at some rate. So if you put a bucket out in the street during a rainstorm and you measure the amount of water that falls in the bucket, and you call that a measure of the rate of rainfall, what you're really doing, the actual number of drops that falls in the bucket is Poisson. It's the probability that the raindrops are falling at that rate, but they're falling randomly, and the probability that they're going to land in that bucket is going to be, the count that will land in that bucket is going to be Poisson distributed. So this is that function, except with an error. This should be e to the minus lambda, so let's write it out again. In fact, I'm going to write it with theta, because that's the variable we're using. So p of k, this is the count, the number of raindrops or spikes, if you're counting neural spikes. So p of k given theta is what? It's, I'm going to need an e to the minus theta, and I'm going to need a theta to the k, and down here I'm going to need a k factorial. And we could spend a little bit of time to derive this, but I don't want to spend that time today. I think it's not worth it. You guys are not going to want to see the extra math, and I think it's not that informative. You can derive this as arriving from various other distributions, and basically it comes about because it's sort of the most random thing you can assume in terms of counts arriving at a given rate. But I'm going to just leave it at that and just give this expression, okay? So the relevant thing is, where does theta show up? Because remember, when we do maximum likelihood, what we're going to be doing is optimizing over theta. So theta's up here in the numerator. There's a theta to the k. This is it kind of looks a little bit like we had a theta to the k in the heads versus tails case, right? And there's also this additional thing, e to the minus theta, an exponential. And then there's a k in the denominator. This is actually k factorial. Okay? So this is just there to normalize the distribution. And in fact, when we go to optimize this over theta, that normalization is not going to matter because there's no theta there. The thetas are in the numerator. Okay? So again, it's useful to take a log, and you can kind of see why. First of all, we have theta to the k. When we take a log of that, it'll pull the k down and give us a log of theta. Also, we have an exponential. That's nice, because when you take a log of that, you're just going to get theta by itself. Okay? So now we do log of, and let's do, now again, imagine that you have multiple measurements. So you're a neurophysiologist, you're recording with an electrode from one neuron, and in an animal that's performing some task, and you take some 100 millisecond interval right when they're doing the task, and you make 100 different measurements of that, repeat the experiment 100 times, and each time you take the number of spikes that showed up in that interval. Okay, so those are k sub n, because I have n trials. So this is the log. I want to write the log of the sum over the trials of the log of the probability of k sub n given theta, where these are the k sub n is the count of spikes on the nth trial, right? And how do I write that out? That's going to be the sum over n of, let's take the log of that. So I'm going to have k times log of theta. And then I'm going to have minus theta, right? That's my log of p of k sub n given theta. And technically, I also have a minus log of k factorial, but I'm kind of leaving that out because I know that's not going to matter, because I'm now going to differentiate this with respect to theta, and that log of k factorial doesn't have any theta in it, so that term isn't going to matter.
It's also not going to matter because you're maximizing over theta. Adding a constant doesn't change which theta maximizes.
Yeah. I mean, we could write it in just for completeness, okay? So here we have a minus log of k factorial, just so we see that it's there, okay? So you don't wonder what happened to it when you're looking at your notes later, okay? So there it is. There's three things here. It's a product of these two divided by that one. When we take a log, that turns into a sum of three things, or a difference of three things, and here they are, okay? And each of those is nicely worked out with the log to give us something pleasant. So that's what we get. Now we take the derivative with respect to zero. With respect to zero.
And those are k sub n's.
Derivative with respect to theta. Say it again.
Those are k sub n's because
Thank
you
you.
decided at trial.
K sub n. That's right, for the nth trial. And we're summing these over n. And now I take the derivative with respect to theta, and I set that equal to 0. So just like I did before. So 0 equals the sum over n of, differentiated with the sum. What's the derivative of the first term? K sub n over theta, right? The derivative of log is 1 over theta. What's the derivative of the second term? The derivative of theta with respect to theta, nobody knows. The derivative of the theta, how does theta change as theta changes? How else can I put this? Does theta change if theta changes? Theta changes as much as theta changes, if it changes. The derivative of theta with respect to theta is 1.
That's inside.
Yeah, I had all those nice ways of saying
Yeah,
it.
that's inside the sum. Just
Yes,
to
it is inside the sum. Actually, let me move that parenthesis. That would help, because that's going to matter. Okay.
And the third term went away because you just took it.
And the third term went away because I differentiated with respect to theta, and there's no theta there, so goodbye. Okay. So now, what do I get? I'm summing this over n, right? Let's say there are capital N of these. I didn't write that, but let's say this is from n equals, I'll put it in here, n equals 1 up to capital N, okay? So then this is going to be, I just switched markers, I should have done that before. This will be the sum over the case of n's over theta. Right? I'm just moving the sum up into the numerator here. And it's minus the sum over the ones. There are n of them. If I add up 1 n times, I get n. So I get minus n here. And that means, of course, this implies what? What is theta hat? If I set this equal to 0, this sum, the sum of the counts over all my trials, divided by theta, minus n equals 0. So put the n on the other side, multiply the theta through, divide by the n, what do I get? Theta hat equals? Yeah. We'll write it out. The sum of the case of n's over capital N, and what is that? That's just the average number of the counts, right? These are different counts for each trial, and this is like, oh geez, after all that work, the answer is, take the average. Seriously? Yes, seriously. That's the answer. The maximum likelihood, nobody said the maximum likelihood estimator had to give us a different answer than the sample average. And here it is, the sample average. So, and sometimes that's how it turns out. If you're doing Gaussian measurements, and we'll show that one in a second, and you ask what is the maximum likelihood estimator of the mean, the answer is the sample average. So this is not inconsistent with all that stuff we did with sample averages. In fact, it's just a generalization. Sometimes it gives you the sample average, sometimes it doesn't. Sometimes it gives you something different. And you have to kind of think through, okay, what is it that I should do? All right.
So
for Poisson,
on the slide is for one trial instead of n trials.
Right, so which is a little bit of a weird case, right? But yes, this is like estimating the probability of heads off of one coin flip. If I flip heads, I say, yep, always gives heads. And if I flip tails, I say, no, never gives heads. It's a little bit of a weird thing to do, but yes, you can do it. You can write the math and you do it. Okay. So we have this example, and it's just the sample average. Oh, it's after 11. Let's take a brief break, and then we'll go back and we'll do some more. Sorry. I need an extension cord in here. All right, so this is just a reminder for the form of a Gaussian, another very standard distribution. And now we can imagine the case of drawing samples from a Gaussian, writing down the likelihood for that. Writing down the likelihood for what? Writing down the likelihood for, well, there's two parameters, right? Gaussian has two parameters. There's mu and there's sigma. They show up, as you know, the mu shows up here. It's the x minus mu. The sigma shows up here. That's the standard deviation. And it also shows up out here. The reason it's out here is because you need to normalize this curve, this exponential. So if you spread the thing out in terms of width, you also have to divide by that width in order to have it integrate to 1, right? So that's why there's a sigma down here. It looks like sigma squared, but it's under a square root. Okay, so now, oh, and I already wrote it here. How convenient. And I even wrote the negative log likelihood here. Oh, that's convenient too. Okay, I left out the mu. But I think what we're going to do, I'm not going to drag you through writing this out because it's pretty simple to write out. If you want to convince yourself, you can try to write it on a piece of paper. If you want to estimate the mean of a Gaussian, given samples from that Gaussian, you write down the likelihood. We already did that. Here it is. Here's the negative log likelihood. And you set this thing equal to 0, just as I did. You take the derivative and set it equal to 0. Take the derivative with respect to the mean, set it equal to 0. And you solve, and what you get is, well, again, it's not a surprise. What you get is the sample average. So your estimate of the mean, mu hat, is the sum of the x's that you observe divided by n. And when you do the same thing for the standard deviation or the variance, you also get the sample variance, right? So this is the sum of each of these variables minus the mean, minus the estimate of the mean, squared and divided by n. Then you can go back and you can ask, well, are these things unbiased? Right? So remember, we can assess estimators in terms of their bias and in terms of their variance. And we can talk about what those are. And we're going to talk about variance in just a minute. You know already, because we talked about it a fair amount, how to assess the variance of this estimator. That's what the standard error of the mean is about. But let's think about bias. It turns out if you estimate the bias of this, it's 0. So why is that? If I take mu hat and I subtract it off from the true mu, and I ask what's the expected value of that, right? That's how you assess bias. You ask, on average, expected value, on average, if I did this over infinite amounts of data, infinite collections of data. So here's a collection of data, n data points, right? I estimate this sample mean, and that's my estimate of mu. If I were to repeat that experiment, gather another n data points, do it again. Gather another n data points, do it again. Gather another n data points, do that a whole bunch of times. I'm not going to get the same estimate every time, right? It's going to flop around. And I could do that in simulation. I could do that 10,000 times on a computer, and I would have 10,000 different estimates, and they would be bouncing around. And I could look at that distribution of estimates, and I could ask, like, where is it on average? Where is its center? And how wide is it? Okay. And given that we're assuming a model here, we don't have to do that simulation. We can actually write down what do we expect the error to be in this on average. And we do that by actually computing the expected value, that is integrating over the probability model. So let's write that down. So I want to compute the expected value. So we're going to compute the bias, right? So I compute the expected value of mu, the true mu, minus, actually I guess I want it the other way. Yeah, let's write it the other way. I want mu hat minus mu, right? So the idea is a positive bias means that my estimate is coming out too high. And a negative bias would mean my estimate's coming out too low, and a zero bias means my estimate's coming out just right. And this is expected value. This is not on any particular set of data. When I run this on any particular set of data, it's not going to come out right. It's going to be flopping around, right? My question is not what happens on any particular set of data, but if I were to imagine infinite sets of data, this is like in data always of length n. I have n samples in my data, but I'm going to gather lots of those. If I had an infinite number of those, on average, does this thing come out right? Okay, that's bias. Right? So I want to compute this thing, and this is equal to, my mu hat is just the sum of my data points. It's right there. It's the sample average. We're using I as an index, and sum of these like this, minus mu. And now what do I do? Well, what am I taking an expected value over? Expected value means compute the average of this thing. Mu is a parameter. It's a fixed value. So the average of this thing is the expected value of this thing is the difference of two numbers. And so it's the expected value of this thing minus the expected value of this thing. But this thing is just a constant, so the expected value of mu is mu. And what is the expected value of this thing? Well, that's equal to, the expected value is a linear operation. We said that in earlier things when we were talking about probability. So the expected value of a sum divided by n is just 1 over n times the sum of the expected values. So it's the sum of the expected values of each of the x's divided by n minus mu. Okay, so all I did here is take this expected value and push it inside all of that to the place where the random variable lives. The random variable here is the x. That's the thing that's sampled in the experiment. But what I want to know is, on average, when I sample this random variable n times, does this thing come out to 0? And you can see almost immediately that the answer is yes. So what is the expected value of x, where x is a sample drawn from this Gaussian distribution? Well, I mean, it's kind of previous slide, I guess. It's a Gaussian distribution, and the mean of the Gaussian distribution is mu. So the expected value of x is just mu, right? That's what the distribution tells me. So this is a situation where I know the distribution, so I can write down the bias. I know the right answer. And so this expected value of the xi's is mu for every xi. It doesn't matter which sample. They're all coming from the same distribution, so they all have the same mean. And so this is really just mu. And there's a sum of n of these. So there's n times mu, because I'm going to add them up n times. And then I'm going to divide them by n. And then I'm going to subtract mu. And of course, that whole thing is 0. OK, check. That's a lot of work and fussing to just make a simple point. This thing is not biased. It's unbiased. And it has a variance, and we know what the variance is. The variance is, anybody want to say what is the variance of this estimate? You know this because we've gone through it with sample averages. What's the variance of that? Right, sigma squared over n. So it's the variance of the Gaussian, that's the source, but it's divided by n because, of course, the variance of this estimate goes down the more data I have, right? I get closer and closer to the true mean, the true mu. Okay, so the variance, the bias and the variance are taken care of here. This thing has 0 bias, and it has a variance which falls as 1 over n. It's sigma squared over n. Okay. Now what about this thing? It turns out that this thing, when you write it down, this is biased. So let's look at that. So let's look at the bias, but now we're going to look at the bias not of the sample average. We're going to look at the bias of the sample. Fingers are getting black. Yeah, I put it down there and I forgot. Okay. So my fingers are getting blacker and blacker. Okay. As I erase bits. Okay, so now we're going to look at the bias of sigma hat squared. Okay, so let's write that out. Let's see. I guess I'll try to stick to that notation. I'd written it down differently here, but that's okay. We'll manage. Let's write it out. So I have the sum of the x's, the xi's, minus x bar. I guess we'll stick with x bar. X bar is the sample average. It's actually mu hat on that slide. Okay? I have the sum of those, and then I have to do what? I have to square them, right? And I have to divide by n. So now I'd like to understand what is the expected value of that. And what I'm trying to figure out is the expected value of that equal to sigma squared? If in that case, this is an unbiased estimator, right? It's the same thing I said about the mean. If I gather sets of n data points, and I compute this thing, I get a number each time I do that, and I drew that lots and lots and lots of times, I'll get a distribution of those numbers. What I want to know is the center of that distribution equal to the true thing? Am I coming out, on average, at the right place? Or does it tend to be systematically a little too big or a little too small? That's what I want to know. If it comes out in the right place, then it's unbiased. All right? So what I'm going to do is I'm going to compute the expected value of this thing, and I want to know, does it come out right? So how do I do that? Again, the only random variable in here, actually there's two random variables in here. The x bar is a random variable because that's the sum of the x's, and the x's are random variables. Okay? So this is actually computed as a sum over the x's divided by n. Right? That's what x bar is. All right, so if we're going to write this out, I'm going to need a little space. How many of you seen this before? Anybody? the bias of an estimate of the variance? One of you. Half of you. Half of one of you is actually what I meant. All right, which half of you is seen? Is it the left brain or the right brain? Right. So, how do I write this? We're going to expand this quadratic thing out. We're going to write this. We're going to write xi minus x bar plus, it's going to look a little silly when I first write it, but you'll see why we're doing it, x bar minus mu. Sorry, I said that wrong.
Xi minus mu plus mu minus x bar is what you have to do.
That's what I meant to do. But in my notes, I have everything kind of switched around, so I'm already slightly confused, but that's okay. We'll figure it out. We're going to figure it out as we go. There. And there's a 1 over n out in front. I'm going to put that here.
You left out the expected.
And I need an expectation. Oh, that's a lot of parentheses. Okay, but let's concentrate on what I actually did. Most of that was not that easy. What I actually did is I took xi minus x bar and I inserted in the middle of it plus mu and minus mu, and I separated that out. So I wrote xi minus mu, and then I wrote mu minus x bar. And of course, if you were to add those two things together, the mu's cancel and you're back to where you were. So I didn't do anything. I just kind of spread this thing out into two pieces by inserting a mu and a minus mu. Why did I do that? Well, expected value 1 over n. Now I'm going to square this thing, and it's a sum of two terms. Each one is a difference. And when I square that, what am I going to get? I'm going to get one thing that looks like x minus mu squared, and then I'm going to get another sum here, which is xi minus mu times mu minus x bar. And then I'm going to get one more. There's two of these. And then I'm going to get a sum of mu minus x bar squared. Right? So nothing fancy here. This is just the square of sum of two terms, and I'm just writing them out. Okay, now we can kind of reason about each of these terms. This is kind of the point. So what do we have? Let's do the first one. What's the expected value of this thing? So x is a sample from a Gaussian random variable. That's the random variable. X is a sample. And what's the expected value of that sample minus the mean squared? Any guesses? I'm just going inside the 1 over n and the sum. I'm just looking at this thing squared. Well, what is that? I have a random variable x. I subtract off its mean, the true mean. This is not some estimate of the mean. This is the real mean, mu. The mean of the Gaussian. I square that thing. And what is that on it? If I average, or I take the expected value of that, what is it? That's the variance. That is the variance. It's like the definition, right? The variance is just take my random variable, subtract off the mean, square that, and then take the expected value of that. That is the variance. So this is the variance, and of course, I'm going to sum this up over these guys. These are independent samples, so the variances add. I've got n of them. So I'm going to get n times the variance here. Oh, and I've got a 1 over n out in front. So that thing altogether gives me just the variance. The real variance, the true variance of the Gaussian. No messing around. Okay? Now, what about the next term? I have 2 times the sum over this thing times this thing. is a product of two things. Here's my random variable. What's the average of this? The average of x minus mu. Average. It's 0, because the average of x is mu. So this term's going to go away. This term, the expected value of this term is going to be 0. And I have one more term. Now I have the expected value of this. Mu minus x bar squared. I have a feeling I've messed something up. Make sure that I didn't.
Why does the middle term?
Yeah, why is the middle term 0? It's not.
Yeah, I think
they're
I
not
did that
constants.
wrong. Did I do that wrong?
Yeah, I think so.
Right. So where's the error? Somebody help me. There's an orthogonalization thing here.
You may need to write mu minus x bar as the average of mu minus x bar.
Yeah. That'll help it. That'll fix it. Indeed. Take b minus x bar and write it as a sum.
Why is that going to help me?
Because then you're going to get one where there's an xi and an xi, and it'll look like a variance, and the others where it's xi's and xj's. It'll go away. Because they're independent.
Yeah. I'm not seeing it. I mean, I'm not seeing it in a simple way. I'm trying to see a simple way to express that. Yeah, this is not obvious. I see how to do this term, but I'm confused about this. Maybe we should put this on hold, and we'll fix it next time. I think that's the thing to do, because if I go down a path that makes it messy, then we will all regret it. So let me just fix it next time. Right. All right.
I have something else I want to fix next time anyway,
Yeah,
so
right.
it'll be fine. We can have
Next
a
time we're going
beginning
to
of
start
fixes.
with some repairs. Okay, let's go on to this statement, because I wanted to do this. All right. So I told you we would get to this, and I didn't start with this. I thought we could go through what is a maximum likelihood estimator, how do we actually compute one, and then come back and tell you a little bit about them and why people use them. So these are sort of technical properties, mathematical properties of maximum likelihood estimation that are usually used as the justification. So the first statement is that the maximum likelihood estimator, I was just about to show you that maximum likelihood estimators are not always unbiased. And in fact, for this case of estimating the variance, the maximum likelihood estimator is slightly biased. And the answer, we didn't get the answer in the end, but it's going to turn out that this thing is sigma squared plus sigma squared over n. So there's a bias. The answer doesn't come out to be sigma squared. It comes out to be sigma squared plus a little bit of something that's not right. It's supposed to give you sigma squared, but it's not. So you're going to get this.
Isn't minus?
Yes, thank you. Thank you. Thank you, Shinyuan. Yes, it's negative. So the estimate that you get is comes out a little too small.
By that much.
Pardon me?
Yeah, what you have there is correct.
Yeah, minus sigma squared over n. Okay, so the answer is you get the right thing minus a little something. But you notice, so first of all, this can be corrected, and the correction, well, I'll do this next time when we explain how you derive it, but the correction is very simple. You make an unbiased estimator by just doing this, doing the sum of your data, xi minus x bar squared, and you divide by n minus 1. So probably a lot of you have seen that. You've seen that when you go to estimate a
sigma unbiased squared.
Squared.
And it's something on previous slides from me you've seen written as s squared from last time.
Okay. So why is it n minus 1 instead of n? And the answer is because if you divide by n minus 1, that's not the maximum likelihood estimate, but it is an unbiased estimate.
And you can
because
see
the
it's
maximum
left
likelihood estimate has this little bit of bias in it. So you can actually fix it, correct it by this rescaling the estimate. Okay? So that's the outcome of all of this is maximum likelihood gives you a biased estimate, but you can correct it. The other thing to say, which is relevant for the slide, is that maximum likelihood estimation is basically guaranteed to be unbiased asymptotically. So that is, the more data you have, if it has a bias, it will go away. And you can see that in this case, because here, the bias is this piece. The right answer is sigma squared, but you're not going to get sigma squared, you're going to get sigma squared minus this little piece, and this will go away if you gather more data. The n is going to grow, and as n grows, this thing will get smaller and smaller and smaller, and eventually, you can basically make it disappear asymptotically in the limit as you have lots of data. This thing goes away, and you get the right answer. Okay, so maximum likelihood estimation is asymptotically unbiased under pretty general conditions. Basically, for all distributions that you're going to care about, that's going to be true. But that's the problem is that that's only useful if the likelihood model is correct. That is, you actually know you've derived a likelihood and the maximum of that likelihood, and it's the right likelihood. That is, it's the correct description of the distribution that generated your data. If it's not, then that doesn't, you haven't really proved anything. It's only true if you can actually compute the optimum. So we talked about the fact that here we're writing these things down in closed form when we write down these maximum likelihood estimates. But in real problems, often they're very complicated, and you actually can't compute the maximum likelihood estimate. And you have to approximate it. You have to use numerical procedures to try to find it, etc. And it'll only be useful or correct if you have lots and lots of data, i.e. in the limit. Okay, so it's generally, this is what people rely on, but kind of these are little warnings, right? Everybody says, oh, it's asymptotically unbiased, and therefore that's what I'm going to use. But, asymptotically, i.e. you need a lot of data, potentially. This is only relevant if you've got the right model to begin with, and you have to be able to compute it. Okay, so maximum likelihood estimation, even though everybody uses it and everybody points to things like this as the reason, keep in mind these little footnotes that you could be in a situation where actually it's not the right thing to do because this is not true. Okay. It's even stronger than that it's asymptotically unbiased. It's not only asymptotically unbiased, but it's actually the shape of the distribution of errors is asymptotically Gaussian. So if you gather more and more data and you keep estimating what does the maximum likelihood estimate look like, and what is the distribution of that estimate, the distribution becomes, as you gather more data, Gaussian. So this is a really remarkable property, and it means that when you talk about errors in your estimates, characterizing those estimates, those errors, with bias and variance is actually a very sensible thing, because what you're doing is you're characterizing the mean and the variance of your estimates. And if it's a Gaussian, the mean and the variance is everything, right? That's the entire description of the distribution is captured by the mean and variance. So you don't have to worry about the fact that the errors might have some funny distribution with a long tail, or multimodal with multiple bumps, or places that are way out in the tails. You don't have to worry about any of that. Asymptotically, the distribution of errors is Gaussian, so all you need to do is to characterize the mean and the variance of that. So all of this fits together, and it's kind of the reason why people talk about bias and variance, and those are the only two things they worry about with estimation. Because asymptotically things are Gaussian, and so bias and variance are really all you need to describe what the distribution of errors looks like. Okay. The last piece is that we have to think about, well, how are you going to compute the confidence? How do you compute the if you like, the variance of the errors? And really, there are 4 different ways to do that. Okay. So the first thing is the thing that, like the most common thing, if the thing you're estimating is just like a sample average, you're estimating the mean, then we already know the answer to this, and it's standard, and you've seen it 100 times, right? That's basically the standard error of the mean. You calculate that, that's the variance of your errors, and then you can use that to make confidence intervals. Like you can take that and multiply it by 1.96, and that'll give you a 95% confidence interval. You can do lots of things with that, but that basically is telling you what the width of the distribution is. Okay? And that works fine if you're estimating means, like using sample variances. If you're doing something more general, you're using maximum likelihood or some other estimator, then what you might do is you say, so I don't know that the likelihood is Gaussian. Let's say I have a finite amount of data, so the likelihood has some funny shape. I don't know exactly what it's going to look like, but I would like to assess somehow how confident I am about my estimate. So here's a standard procedure, an idea. It's very simple to describe, and it shows up in a lot of examples, sort of prior to the modern era. So I just want to describe it to you so you know what it is. And it goes like this, basically. You have this likelihood function, so you plot, imagine that the negative log likelihood, NLL, is some function like this of theta. So here's theta. And let's not make it quite so bad. Let's make it like that. Okay? And your optimum is here, because you're going to minimize now, because it's the negative log likelihood. So here's theta hat. So I go ahead and I find my theta hat. And now I would like to report something. I want error bars. I want to be able to say something about how confident I am, how sure I am about the theta that I just reported, the theta hat. And if you don't have the luxury of assuming this is a Gaussian distribution, because you have a finite amount of data, and this is only Gaussian asymptotically, so I have some finite amount of data, what you're really saying is the shape of this is not parabolic, right? If it's Gaussian, the negative log likelihood looks like an inverse parabola, right? The Gaussian's e to the minus x squared. If I take the log of that, I get minus x squared. If I take the negative of that, I get x squared. So it looks like a parabola. This doesn't look like a parabola. But what I can do is locally do what we would call Taylor approximation. Right? So I already know that the derivative at this location is 0. That's how I found this optimum, by setting the derivative equal to 0. And now what I can do is, and the derivatives, that's the first derivative. Now I can take the second derivative, which measures how the derivative changes as a function of theta. I can take the second derivative, which is going to basically look like, tell me what the curvature of this function is right around the minimum. The second derivative. So I take the log likelihood, we call that negative log likelihood, we call that L of theta. And I take the second derivative, d squared d theta squared. Okay? The second derivative. not the first derivative. The first derivative is 0, because I'm at the bottom here, right? Take the second derivative. That tells me how curved it is. And I can use that as a measure of how confident or certain I am about this choice of theta. Think of it as this way. If it's really steep, then I'm really confident about this. This is in a very sharp valley. If it's very broad, I'm not so sure. Like this can flop all over the place because the difference between the negative log likelihood here and over here is not very much. So the idea is you can measure this quantity, the second derivative of the negative log likelihood, and use that as an estimate of variance. Okay? And all you're really doing is basically treating it. You're not treating the whole distribution like it's Gaussian. You're doing something like a local expansion in a quadratic expression, right? You're going to express this as something that's quadratic, and then you're going to treat it as if it's really just that Gaussian. And then you use the width of that to describe your confidence. Okay, so this is a very standard approximation to use the second derivatives. Use the first derivative to find the minimum, and use the second derivative to describe how confident you are about that minimum.
And
That's this.
Relate that to the Gaussian?
In what sense would you like me to relate that to the Gaussian?
Well, the Gaussian,
That's-
if you take the second derivative of the log, is a quadratic.
Right.
And the constant on it is the
It's
inverse
sigma
variance.
squared. So we can, I've erased it. It was almost up here on the board before. I said it in words and it was almost on here, but you're saying I should write it again, so I'll write
It just gives you a, it
Closer.
takes this odd thing and it connects it to something we
Closer.
already know.
it. Yes. Right. Well, we've gone through several steps here, right? So the first thing, we've gone into negative log likelihood mode. We fit a Taylor approximation. You're describing your function locally as a constant plus a linear term, but the linear term is 0, plus a quadratic term, so you're describing it really as a parabola. And then, of course, if you think what you're really doing is you're describing, probabilistically, you're describing this as a Gaussian, right? Because the second derivative of the log likelihood, if this thing was actually a Gaussian, what would its second derivative be? So it would have e to the minus x squared. I guess we could do x. I'm not going to write out what this is why I didn't write. Okay, let's just do this. Take the second derivative of this.
Just take the negative log of it. See what you get.
Yes, and you need to take the second derivative. We already did the negative log of it. We wrote that out before.
Well, the negative log of it is x squared over 2 sigma squared.
I know
And
that.
so you don't. So then you're done.
If it's Gaussian and you take the negative log likelihood, you get 1. Take the log, you get minus x squared over 2 sigma squared. Take the negative of that, and you get x squared over 2 sigma squared. And now you take the derivative of that with respect to the position x. X is now theta. We just flipped our variables around. And you get the sigma squared. You get 1 over the sigma squared. Which is why I didn't want to say this, because now it. Is everybody fully confused? Or just half confused? Anybody half confused? All right. Let's go. Let me go back to finishing my list, okay? So in multiple dimensions, you can use the same trick. So this is one dimension. We drew this picture. We think about basically a quadratic expansion around this point. If we're in 2 dimensions, what would you do? Well, now you're the negative log likelihood. You're in a 2-dimensional space. You're kind of down in a valley, right? You're at the bottom of the valley. And now what you want to do is you want to describe what's around you when you're sitting at the bottom of the valley as a parabolic bowl, right?
Where 2 dimensions means 2 parameters.
Yes, that's right. So here I'm in theta 1, theta 2 space, okay? And over here is theta hat, which is now a vector, of course. It's this point in the space. And I have around me, let's draw a contour map, right? Right? This is what the negative log likelihood looks like, let's say. Right? It's got some contours at constant value. And I'm down at the bottom of this valley, and I'm looking around me, and I want to express now my uncertainty about this. But it's now a two-dimensional uncertainty. And we know how to express this two-dimensional uncertainty. We have a tool that we've been building ever since we did these squares, and that's the covariance, right? So what I want to do is describe locally, I'm going to approximate this as if it's elliptical. It's not elliptical. I tried to draw it on purpose as if it's got funny contours that are curved, right? But the actual, what I'm going to do is I'm going to expand it again with locally as a quadratic function. A quadratic function in 2 dimensions is just a sum of 3 terms. There's a theta 1 squared term and a theta 2 squared term and a cross term, theta 1, theta 2. And we know how to write that using linear algebra, right? There's a matrix that's going to calculate, that's going to have a bunch of values in it, really 3 values, that are going to control the shape of this quadratic function, right? We know how to write this. It looks like theta times matrix times theta, right? And that function is, we can fit that, and what goes in here are going to be these derivatives. So the second derivative with respect to theta 1, the cross derivative theta 1 d theta 2, and then the second derivative with respect to theta 2, right? We're going to fill that matrix with the second derivatives, and that thing is going to play the same role that this one did, but it's going to capture now the 2-dimensional structure of the error surface, if you like, and it will capture how confident I am about my parameter estimate in these different directions. If this is a long, skinny valley, what does that mean? Well, let's start with, let's say it's circular, and it's a really deep circular valley. So it looks like this, and it comes up out of the board very, very deep. Then I have a lot of confidence, right? If I move just a little bit, the likelihood gets much bigger. So this is a very, very precise estimate of this thing. If it's a very shallow bowl, circular, then I don't have much confidence. What happens, what does it mean if it's like long and skinny? So it's shallow in one direction and it's steep in the other, right? So it looks like this. What does that mean about my estimate? It basically means that I'm very confident about this aspect of my estimate of theta. Theta is a vector, right? It's a 2-dimensional vector. So I'm very confident about this, but I'm not very confident about this. In other words, if I were to change my parameter by wandering off along this valley in this direction, it would be almost as good as the one at the bottom, or in this direction. So I can kind of meander around down here and get pretty good solutions. So I'm not actually very confident about this aspect of my estimate. I'm very confident about that aspect. So we now have not just a variance on our estimate, but a covariance, right? We can describe in any direction we want how confident we are. And we don't now just state a 95% confidence interval. Now what we're going to have to do is sort of draw an ellipse and say, well, this is a description of our confidence in this 2-dimensional space. Okay? So the generalization from the 1D case to the 2D or many-D case is actually completely natural once you know how to think about this using linear algebra and covariances, right? So this just pops right out as the natural generalization of that. And you know even how to do calculations on this. For example, what if I wanted to find the axis of minimal uncertainty? How would you do that? Anybody know what calculation you want to do on this matrix that expresses the covariance? Yeah, an SVD, or find the eigenvectors, right? So there's an eigenvector that has a big variance, and there's an eigenvector that has a small variance, and those 2 directions in the space capture the direction of high confidence and low confidence. Actually, I said those in reverse order. The high variance is low confidence, the low variance is high confidence. Right? So we know how to do those calculations. They're all just the same math we've been doing all along with linear algebra and covariances. So it's just making use of the same tools we already have, but now applying them to this situation. Okay. Yeah.
Inverse of the matrix.
Yes, I was just realizing I didn't express that. So, what's the easy way to express that?
A little minus one.
Thank you. When you calculate this derivative, if this were Gaussian, what comes out is not the variance, but 1 over the variance, right? So what you actually need to do to express confidence intervals, so let's say I wanted 95% confidence interval. What you could do is you take the second derivative of the log likelihood, evaluate it at theta hat. So I'm going to actually evaluate it right at the optimum, right? And then you take 1 over that, right? So I invert that. And you multiply by whatever it is, 1.96.
I called
okay,
that
so-
2 days ago, by the way.
Oh, really?
Yeah, I was being lazy.
All the books seem to write it as 1.96.
Well, 1.96 is correct out of the Z table, but I'm lazy, I write 2.
Okay, so look, this is a variance, or standard deviation, and then, sorry, I have to take a square root, so this is actually minus 1/2, because this thing is a variance, I have to take the square root to get the standard deviation, and then I have to multiply by 1.96 if I want 95% confidence interval, or we can round that to 2, as Mike just said. Okay, so 2 times that would give me a confidence interval. Now what happens if I'm in the 2D case? We're not talking about confidence intervals anymore, but the covariance is, it's actually not a covariance, it's the inverse of the covariance. So what you need to do is, again, it's the equivalent of raising it to the minus 1/2. You have to invert the matrix. You have the covariance, the inverse covariance matrix. That's actually what shows up in a Gaussian, right? If I have X, the covariance is C inverse, right? That's the multidimensional Gaussian over 2, e to the minus, okay? So when I go and I compute the log of this and I take the second derivatives, what do I get? I get C inverse, the inverse of the covariance, i.e., when this thing has a large value, there's some direction where it has a large value, that corresponds to actually a small variance, and when it has a small value, it corresponds to a large variance. So if I want actually covariance, I have to invert the matrix that I get out when I take second derivatives, and then I can go and do all the calculations I want. Okay?
So now you can write little minus 1 over here.
That's what you want.
That's what I wanted. That's all I wanted.
Okay. All right. So, second derivatives. And by the way, the second derivative in multiple dimensions is called the Hessian. The second derivative of a function is called the Hessian, if that means anything to you. It's just a word that you might encounter when people describe this, okay? Well, the second derivative in multiple dimensions is a matrix. You know how to deal with that matrix. It's going to correspond to the inverse covariance matrix, and it will tell you about confidence in the same way that the 1D case does. Okay, so I want to finish this list before we end today, and then we'll fix that thing that I busted next time. So, simulation. So what is that? So this thing is sort of closed form. You just calculate the variance of your data and you divide by n. This thing requires you to do a little bit of work. You have to write down the likelihood function. You have to take second derivatives of the negative log likelihood, and then you have to invert that or treat that like a variance or inverse variance. Invert it, and then you can think about that and use it to calculate errors of work confidences. Okay. What's this? Okay, so in the modern era, we switch into a mode where we use computers to do these things. So this involved writing down derivatives and calculating second derivatives. Simulation. So if I think I know something about the model that generated my data, what I can now do is go back and simulate the model. Once I've done my estimate of parameters, right, I have theta hat, plug that back into the model. Now draw samples from that model lots and lots of times, and look and recompute the estimates each time, and look at the distribution of estimates that I get out of that. So I can actually examine what the distribution of estimates looks like in simulation, and then I can do calculations of how wide is that distribution. I could calculate the standard deviation, or I could calculate, quantiles, or whatever I want. What depends on what the distribution looks like. If it looks kind of Gaussian, then probably I just measure the standard deviation and I'm done. But if it looks kind of weird, irregular, lumpy, heavy tail, asymmetric, whatever it is, I can do a different kind of calculation. So for example, I might calculate, clip off 5% on one side, clip off 5% on the other side, and those two intervals might not be symmetric around my estimate. They might be a little bit to one side and a lot to the other side because the tail is sort of funny, or there's a lump way out there. So you can do calculations that involve simulations on a computer, simulating the model that you think is generating the data, and actually looking at the distribution of estimates that you get out of that. Right? The last thing, which I think we don't have time to do, is called bootstrapping. And that involves essentially combining the idea of simulation with the idea that, well, I don't actually have a model for my data. What I'll do is I'll just do simulations with the data that I have. This is a slightly bizarre idea, and next time I'll explain why it's called bootstrapping and what you actually have to do that. This has been sort of taken over. This is so simple and easy to perform that people are now at a point where they basically just do this and they ignore all of these. I think it's worth actually knowing about all of these different methods and thinking when you're faced with a problem like this, which thing should I be doing? What do I want to rely on? But this is a very simple procedure that is surprisingly reliable. So we'll talk about it.